Good morning, everyone. I request the chair to kindly start the session.
Okay, good morning to everyone. Welcome to Room D and welcome to our virtual and on-site attendees joining us for the ICCSA conference. The topic of this room that are being discussed here are PCIe and IoT and urban planning. We have three papers on the line. Each presentation is strictly allocated in 20 minutes. Please respect the time. I suggest you that use 50 minutes for the presentation, followed by 5 minutes for a brief Q&A. So let us begin. Our first presentation today is going to be about a lightweight crystal dilithium post-quantum cryptography signature for FPGA-based edge computing by Do et al. So I invite the presenting author to share the screen, and now I will now yield the floor to you.
I'm sorry, I cannot see the shared screen. It's all gray.
Okay, it's like on the overlay of the application is near the end sign on the board. Do you have any problem with the presentation? Uh, right now we can't hear you.
I'm not able to see the participants' screen.
Okay.
This one.
And it's this session is now.
Yes.
Yes.
I have to ask him to share
Yeah,
screen.
I think they're already sharing because it says that they're sharing the screen.
Okay.
But I can't see them.
We are seeing only a gray screen.
Shall I ask them to reshare?
Yes, please. It's better to ask to reshare or maybe ask them to change the browser.
Okay.
Okay. Just sometimes it's something related with browser.
Okay. Thank you. Can you please reshare your screen? Or maybe change the browser to Chrome. If you're using Chrome, please change it to Firefox.
So, uh, Doc, can you hear me?
Yes.
Okay, so in order to not waste time, we're gonna swap the first presentation with the second one. So I buy you some times to fix this error. So the second presentation, um, it's it's by Aversano et al. A binning-based approach for intrusion detection and attack classification in the Internet of Medical Team Networks. It's a virtual presentation, and I'm gonna be the speaker of this presentation. So let me share the screen. Okay. So let's start by introducing the field of research where we have worked on. Uh, Basically, the principal research question that we asked ourselves was if we can fill the gap between deep learning and lightweight tabular machine learning in the problem of classifying malicious and being samples in an IOMT settings under an attack scenarios. So basically we want to understand if deep learning architecture, we can take the advantage of the deep learning architectures and use the lightweight tabular machine learning advantages in only one approach. That was our starting idea. The main contribution of this work are the first hybrid IDS-IPS methodology, a supervised binning mechanism that is evaluated under strict protocols, and an evaluation on three public datasets that represent three pillars in this piece of literature. The first one is SIG IMT 2024, the second one is IMT traffic data, and the latter is Visual MS 2020. So let's explain the idea. And the idea is basically that some features are categorical and not ordinal. This is obvious when we are seeing the sample of port in network security. Ports are obviously a categorical feature, but the principal idea that we use in this study is that maybe ports are not the only feature that has this behavior. Like for example, one feature could be the packet length, and it's counterintuitive that something like the packet length is something that has a nonlinear behavior, because under the hypothesis that the dataset is synthetically generated and that is our case, because I remember you that in IOMT scenarios where we need to manage medical data, we can't obviously use data that is real for obvious reasons. And the idea is basically that if we have, for example, a ping sweep, or we have attacks that use packets with low sides with respect to the packet length. The idea is that they create some zones of interest. What does it mean? It means that, for example, a decision tree can easily cut down these zones, but a neural network has a very hard time in doing so, because a neural network needs to approximate a stepwise function. And like you can see on the sample of only one feature vector on the packet length. But if you watch the perspective from a more broad angle, you could understand that by adding more feature with this behavior, that is the problem of this behavior is that it's generated probably by the synthetic generation without proper randomization and proper mechanism to enhance the attacks. This creates zones that are easy to classify and easy to exploit by decision tree or tree-based architecture, like for example XGBoost or CatBoost. They are really good in these scenarios. So the idea is we use binning. We use binning utilizing a tree architecture, so a decision tree, and we take every feature vector and we basically create beans to order the feature. So basically a neural network can easily classify easily can use these beans in a way that the beans are separated from each other, and is an advantage. So in our case, for each top feature, a single feature decision tree places the split threshold that are most informative about the label. We have used the two techniques that we are going to explain later in the slides. And these techniques are basically the most straightforward, the easy ones, because we want to demonstrate that in these scenarios, it's useless using complex architecture, like for example, vision transformers, tabnet, convolutional neural network with big GRU architecture, or BLSTM architecture. And the idea is basically, okay, let's try to create an hybrid approach, utilizing the decision tree to separate beans, and then the textbook architecture that is a simple neural network to create a classification head. Those are our binning variants. The first one can be seen as also a meta-learner, because we basically train a decision tree over only one feature vector to predict the output label. Remember that we only use the train and the validation, so there is no data leakage, because obviously if you, for example, use the decision tree without a validation set, it's an obvious scenario that you're going to do a data leakage and you're going to see the test. So it's we have created a very strict protocol evaluation to evaluate these two binning variants. And the second one is the straightforward, well-known binning by threshold that assign to every bin an index. So basically, the difference between these two architectures is that in one example, we can have bins that have an index greater than 2, and in the first one, we use a bin that has an index value between 0 and 1, Boolean, basically. So we have 3 public IMT dataset, and this dataset represent different scenarios of IOMT anomaly detection. We have, like you can see, that we have small samples cardinality in the VuSLH 2020 with some particular feature that were difficult to process. They require a careful pre-processing step. We go next with the IMT traffic data with a dataset that has a fair amount of samples with a balanced class ratio. If we consider the binary classification, it represents a beautiful dataset because it has co-op and MQTT protocol, and it uses a lot of attacks that are aimed to create zones of interest in these particular studies. The last one represents a pillar in the literature, and it's CKMT 2024 with 9 million samples and 19 classes. This dataset is perfect in our case because it represents a difficult scenario with unbalanced data, and it requires careful processing because, like as you can see, we have data, we have classes that represent 0.01% um, of the data set. We have a 2000 to 1 max to min class ratio, and there is a note to say, and it's the fact that IMT traffic data and Bruce AHMS 2020 are evaluated and they are strict certified five-fold cross-validation and with fixed validation holdout. So outer cross-validation with a fixed validation holdout. Instead, the CKUMT 2024 has a fixed outer script, and we use the fixed outer split to enhance comparative analysis with other work. So the experimental setup, as I said, it's really straightforward. It's simple because the idea of our work was basically to give basically a critique to the literature. It's sufficient to understand the data and not to use like EV architecture without a sense. And basically the idea was to use a standard textbook architecture with batch norm. The epochs are 20 by literature standards. We have a batch size that alternate between 2056 and 64 based on the cardinality of the dataset. The binning key is the 50% of the feature space. So we have only binned the first 20 feature for space reasons. And the model compared are decision tree, neural network, and the hybrid approach that fuses decision tree and the neural network. As you can see, we have used a commercial PC, so it's worth saying that we haven't fully optimized our work, but it's enough to show that the datasets are really simple. The datasets are really simple to classify. They are really a straightforward data set to solve, like not to solve, but in order to give a clear classification. And the only problem was CKMT 2024. But as we have seen in the literature, CKMT 2024 as a great problem is challenging because of the class ratio of the lower minority classes. As you can see, those like this course could be high, but in this particular settings and in these scenarios of the literature, these scores are pretty normal, and that's our way to say that standard procedure, standard models, for example, machine learning algorithm, also the tree, also normal random forest, the gradient boosting method, the XGBoost, the CatBoost, performs well. And the idea is basically, okay, but what is the advantages of combining non-linear behavior of the decision tree with the decision tree architecture with the non-linear behavior of the neural network? Is that now we have an inference style that is obviously really advantageous. And the idea is, as you can see, we have a weighted F1 that is really high. The F1 macro is the most important metric, but the idea is that what we want to highlight is the inference time that is around 10 seconds per sample, 10 milliseconds per samples. So we have created a comparative analysis against the literature. As you can see, the literature doesn't report scores on inference time. The principal reason is that firstly, our study was the first one that created a framework, a robust framework to evaluate with standard deviation and multiple runs per task in order to create a fixed confidence interval where we can evaluate our mechanism or solution and understand what is the advantages of our solution. But the literature didn't care because honestly, there is the literature is in a embryonic phase where the idea is to perform, to score. But the final conclusion of our work is that score are already it's useless that we start trying and saturate the data set. We want to understand we want to understand if we can do something also for a real case deployable scenario, and that is our major point, our major strong point on the literature. We have faster methods, and we have faster methods with easy and reproducible ways to create mechanism that works on single nodes that on IoT scenarios are really important. So this is the real time on a single CPU. As you can see, the only variation is on Brussels AHMS 2020. The principal reason is because on this particular dataset, the pre-processing step require a lot and careful balance because we have string values and a lot of normalization that is needed in order to perform with high score on this dataset. And obviously, the literature didn't report the inference time, but it's obvious that between a textbook architecture that uses decision tree and a neural network with around 200 nodes, like a Vision Transformer, a Tabnet, or a Big Ruby STM, is gonna be EV, is not gonna be capable of reaching this inference time. So these are our conclusion. We have created an architecture that's hybrid by design. It's interesting from a theoretical perspective to understand how can decision tree can be exploited in these settings, in general on anomaly detection settings, and we have demonstrated that instead of saturating the data set with metrics that are basically every time 0.99, the best idea that one could use is to start working on real-time deployment on single nodes or multi-node architecture. It depends on the hospital settings. And we are creating this architecture that basically combines all these advantages. It's an easy architecture, but it's from the simple idea that it's sufficient to understand the data and not use complex architecture without understanding what is the settings of the IoT network. So this is this is our prior work. If you have some question, I'm here to answer them. So do someone have some question?
Yes, I have a question. Did you try using explainability technique for the model?
No, because at the end, the neural network creates a nonlinear behavior. So it could be used, for example, shock values, but the objective of our work was only inference time and training time efficiency. But it's a nice point, a nice perspective point. And we also had this idea because by splitting into beans, theoretically, you have an easier work to understand if there are some beans that contribute better in the backpropagation loss instead of other beans. But as we said, it's something that we are gonna probably understand later with successive work.
Okay, thank you.
So for the second presentation, uh, if do you um, like do you have fixed the have you fixed the problem with the presentation?
She has sent me the presentation. If it's okay, I can share.
Okay.
Hello,
Hello.
I think I'm able to share it now. Oh my, hello.
Hello, we hear you, and we see the presentation.
Okay, I will prepare my presentation now. Sorry for the inconvenience.
It's okay. It's okay. You can start the presentation.
Okay, good morning everyone. My name is Huy Minh Dung Do from Ho Chi Minh City University of Technology, Vietnam. It is my pleasure to present our work entitled A Lightweight Crystal Dilithium Post-Quantum Cryptography Signature for FPGA-based Edge Computing. This is the outline of the presentation. First, let's start with the motivation of this research. As quantum computing continues to evolve, conventional public key cryptographic algorithms such as RSA or elliptic curve cryptography are expected to become vulnerable to quantum attacks. Therefore, there is an increasing demand for post-quantum cryptography to ensure long-term security. Among the post-quantum digital signature schemes standardized by National Institute of Standards and Technology, modulated-based algorithm has emerged as one of the leading candidates. However, deploying MLDSA on edge computing platforms remain challenging. Edge devices usually have limited computing resources, memory capacity, and power budgets. At the same time, MLDSA requires several computationally intensive operations, such as number theoretic transform, check hashing, and rejection sampling. Furthermore, when implemented on an NOC platform, communication between the processor and the FPGA accelerator also introduced additional overhead. Therefore, the goal of this work is to design a lightweight FPGA-based MLDSA signature engine that reduces signing and verification latency while maintaining a compact hardware footprint, making post-quantum authentication more practical for FPGA-based edge computing. With this motivation in mind, let me first introduce the background of the modulated-based digital signature algorithm and the research gap that inspired our proposed design. As first, MLDSA, formerly known as crystal dilithium, is a standardized post-quantum digital signature algorithm defined in the Federal Information Processing Standard 204. It provides the authentication, integrity, and non-repudiation, while its security relies on the hardness of the module lattice problems. MLDSA defines three standardized parameter sets with different security levels. In this work, we focus on MLDSA H7, which provides challenging target for FPGA, which, which provide the highest security and I'm so sorry. We focus on MLDSA A7, which provides the highest standardized security level. It also has the largest computational workload, making it a representative and challenging target for FPGA acceleration in edge computing. At the implementation level, MLDSA performs polynomial arithmetic over a ring finite polynomial. To efficiently compute polynomial multiplication, it heavily relies on the number theoretic transform entity together with the inverse entity. The dominant computation kernels, including entity and inverse entity for polynomial multiplication, pairwise modular multiplication, check-based hashing for seed expansion, and coefficient sampling, rejection sampling during signature generation, and encoding or decoding operations for key pair and signature formatting. From a hardware perspective, arithmetic-intensive operations such as entity are well suited for FPGA acceleration, while control-intensive tasks can remain on the embedded processor. This naturally motivates a hardware-software co-design approach. Previous studies mainly follow four directions. Some focus on accelerating only the entity kernel, achieving high performance, but without optimizing the complete signature workflow. Others implement the intra-dilithium algorithm in hardware, providing low latency at the expense of increased hardware complexity and reduced flexibility. Some design target high throughput batch processing rather than low latency edge application. Finally, hardware-software co-design approaches improve flexibility, but communication overhead between the processor and programmable logic remain a challenge. Therefore, there is still a need for a lightweight implementation that achieves three objectives simultaneously: compact resource utilization, low end-to-end signing and verification latency, and efficient communication between the processor and the FPGA accelerator on a realistic SoC platform. To address this research gap, our work makes three main contributions. First, we proposed a lightweight FPGA-based MLDSA engine optimized for resource-efficient signing and verification. Second, we implement and validate the complete design on the Silicon Carrier SoC platform, integrating an ARM Cortex processor with programmable logic. Finally, we perform a comprehensive experimental evaluation, including hardware resource utilization, power consumption, latency, throughput, and comparison with software implementation. Having established the research gap and our main contribution, I will now move to the core of the presentation, the proposed FPGA architecture. Our implementation is built on the Silicon Carrier platform, which consists of two main components: the processing system, PS, and the programmable logic, PL. The PS is an ARM Cortex processor running PinQ. It provides the software interface and APIs for controlling the accelerator, preparing the input data, issuing execution requests, and observing the execution results. Communication between PS and the PL is mainly performed through the AC protocol, which provides an efficient interface for transferring control commands and data. The PL is the main focus of this work. It receives the required inputs, such as seeds, messages, or signatures in the verification phase, and executes the requested dilithium operation, including key generation, signing, or verification. Having seen the system-level architecture, let's now look inside the FPGA accelerator. The accelerator is organized around a global controller. Whenever the processor sends an execution request through the AC interface, the global controller starts the corresponding workflow, whether it is key generation, signing, or verification. During execution, the controller coordinates the major computation modules and manages the overall execution sequence. Intermediate polynomial data are stored on chip DRAM, while the computation-intensive kernels are delegated to dedicated hardware modules. Among these modules, The entity engine is one of the most performance critical components. We build a Redis for entity by combining 4 Redis to butterfly core. This organization allows 4 coefficients to be processed simultaneously, improving computational parallelism while maintaining a regular hardware structure. In addition, we introduced a pipeline data path so that multiple polynomial operations can be processed continuously, improving the overall throughput of the accelerator. The complete polynomial operation module integrates all computations related to polynomial arithmetic. Its computation controller schedule both entity and inverse entity execution according to the requested operation. The address generator unit generates memory address for multiple VRAM banks while also providing the correct tweet vector addresses. This organization to avoid memory access conflicts and enable efficient parallel execution. The Redis to multiply to butterfly block performs the core modular arithmetic, including butterfly computation during entity and inverse entity. Finally, after inverse transform, the post-inverse entity module performs inverse scaling and converts the parallel computation results into serialized output data using a PISO interface. Besides polynomial arithmetic, MLDSA also requires efficient polynomial sampling. For this purpose, we designed a dedicated sampling model. This model expands the input seed using the shape paste function and generates the different types of polynomial required by the algorithm, including the public matrix A, the secret vector S, masking vector Y, and challenge polynomial C. With these dedicated hardware modules working together under the control of the global controller, our accelerator efficiently executes the computation-intensive kernels of crystal dilithium while leaving control-oriented tasks to the embedded processor. Having introduced the architecture of our accelerator, I will now move on to the synthesis results and experimental evaluation. First, let me briefly describe our experimental setup. We evaluate the proposed accelerator on the Selene Carrier KV platform and compare it against the MLDSA software implementation running on an ARM Cortex-A53 processor to ensure a fair comparison. Both hardware and software use the same test vector. We evaluate not only the complete phases, but also the major computation kernels, including entity, identity, polynomial multiplication, and polynomial sampling. Besides latency and throughput, we also report hardware resource utilization and power consumption. Let us look at the synthesis results. As shown on this slide, the accelerator occupies approximately 83% of the available LUT resources while using only a small fraction of the available DSP block. This indicates that our design is mainly logic intensive because polynomial arithmetic and shape-based sampling are implemented primarily on configurable logic rather than dedicated multipliers. In addition, VRAM resources are efficiently utilized for storing intermediate polynomial data, while the design operates at a maximum frequency of 133 MHz with a total power consumption of 3.71 watts. Overall, these results demonstrate that the proposed architecture achieves a compact implementation suitable for FPGA-based platform. Move to the performance result. The proposed accelerator consistently outperformed the software implementation across all major operations. For the complete workflow, we achieved a speedup of 3.66, 4.56, and 4.18 for the verification scheme. If we look at the computation kernels, the improvement is even more significant. The entity and inverse entity achieve approximately 12 to 40 times acceleration, while polynomial multiplication reaches about 11 times speed up. These results These results clearly indicate that the arithmetic-intensive kernels benefit the most from the FPGA parallelism and parallel execution, which directly translate into lower end-to-end latency for the complex signature process. Finally, let us compare our entity implementation with several recent FPGA-based design reported in the literature. Although some high-performance implementation achieve slightly lower latency, they are generally optimized specifically for the entity kernel or target larger on more resources-intensive platform. In contrast, our implementation is designed as part of a complete lightweight dilithium accelerator for edge computing. Despite this broader design objective, our entity latency is only 1.93 microseconds with a polynomial multiplication latency of 0.48 microseconds, demonstrating competitive performance while maintaining a lightweight hardware architecture. These experimental results confirm that our hardware-software co-design successfully balance resource efficiency, execution latency, and practical deployment on the FPGA-based edge platform. With the experimental evaluation completed, I will now conclude this presentation with the main findings of our work. In this work, we propose a lightweight FPGA-based MLDSA accelerator for edge computing applications. Our architecture combines an ARM Cortex processor with a dedicated hardware MLDSA hardware accelerator through a hardware-software co-design approach. By accelerating the computation-intensive kernel in hardware while keep control-oriented tasks on the processor, the proposed design achieves port flexibility and efficiency. Experimental results demonstrate significant performance improvements over the software implementation, with up to 4.56 times speedup for the complete signing operation and approximately 12 times acceleration for the entity kernel, while maintaining a compact hardware footprint suitable for resource-constrained edge platforms. Overall, this work demonstrates that post-quantum digital signatures can be efficiently deployed on FPGA-based edge computing systems, providing a practical solution for future secure embedded application. Thank you very much for the attention. Now you can ask directly or scan the QR for any question and feedback.
Okay, so thank you for your presentation. I ask if there are any questions from the local audience in room D or from the participants here in virtual. If there aren't any, we can go forward on the third and last one presentation. So are there any questions? Okay, I think that there are no questions. So the last presentation of today's session is by Vilotta et al. Snap4 City, SUMI Manager, a digital twin integrated framework for sustainable urban mobility indicator processing and visualization. The type of the presentation is in presence. And the floor is now yours, so you can start by sharing your screen and presenting your slides.
Do you want me to switch the camera to you?
No, it's okay. Okay, you can switch it. Switch it.
It's not yet showing.
Okay. So perfect. Hi everyone. Thanks for having me for this conference. I am Enrico Collini and I will present this work that been developed me with my colleagues from the Disease Lab from the University of Florence. Today I will present the solution for monitoring these urban mobility KPIs. So briefly, we have a growing challenge for modern cities since the city population density is rapidly increasing. More and more people are living no more in rural areas, but they're going to the cities for services, work, and so on. So from some data, urban population growth is around 1.5 up to 3%. Meanwhile, the CTR expansion with the buildings and so on is around 0.2 to 0.5%. So the trend is that population density in the cities is rapidly increasing. In Italy, Naples is the most highly density populated city with almost 8,000 residents per square kilometer. So this causes mobility stress into the cities. This in the image is Naples. So the problem is that we have traffic congestion if the road network is not optimized. We have also environmental impact on pollutants and both air and noise pollution. And of course, we have also safety aspect about the road accidents. From data of mobility by TomTom, as you can see, we have Naples, where people stay in the queue 90 hours per year, and Florence, where our university is from, that is less density populated than Naples, has 113 hours of queue in traffic for commuting to work. So this is critical also for less density, highly densely populated cities. And decision makers propose or are trying to solve this problem, proposing a lot of intervention, like promoting active mobility alternative, sharing, and so on. They try to optimize the current road infrastructure. They try to limit some mobility partners for certain type of vehicles. And also, of course, the intervention focus on the digitization of the city infrastructure, installing sensors, and developing this kind of mobility digital twin. The challenge is how to monitor these intervention outcomes. One of the possible solutions is to exploit some data-driven KPIs in order to see if the interventions actually improve this challenge for modern cities. A data-driven urban mobility solution should support urban mobility planning, should enable comparison across different cities and across different periods, across different time periods. Even more, this solution should enable multi-sector KPIs from environmental pollution, social aspects, accessibility, economic aspects as well as the, for example, public transport costs. And so we are aiming to have some standardized KPIs, so key performance indicators, to compare cities to track the progress of the improvements in the urban mobility interventions. The problem is that in order to have this kind of solution, data collection can be challenging depending on which city and which data you have. The computation may require multiple data sources, heterogeneous data sources that you need to integrate. So you need a big data management platform to have time series historical analysis as well as cross-city evaluation. And it's pretty difficult to compare different cities, both because they may have a different kind of data. But if you are able to have these standardized KPIs, you can do that. You need, of course, a big data platform to enable decision makers to assess these KPIs. Fortunately for us, the European Commission introduced the SUMI, Sustainable Urban Mobility Indicators, in order to have a coherent possibility to analyze the urban mobility situation in different cities, and even more to assess the effectiveness of urban interventions. These are 18 key performance indicators ranging from social equity and transport accessibility, like this one. Maybe with this I can use the laser, like the affordability of public transport. This is the first SUMI indicator that corresponds to the budget that the poorest quartile, so the poorest 25% of the population, required to purchase the public transport passes to go everywhere in the city for all the family in the urban area of residence. Next, this SUMI can cover environmental, of course, pollution, noise pollution, energy footprint, and now we will see some more details. Operational safety, like we have an indicator, if I remember, on the number of deaths. Health related, so promoting also active mobility, like the kilometers of cycle paths, as well as accessibility and space. So in the next slide, I will briefly present 10 of the 18 SUMI indicators, because once now I'm presenting, I do not have a lot of time, and then the table didn't fit in the slide. So we can see we have S1 affordability of the poorest group. And in this table, it is highlighted the complexity of the required data type in order to have the computing of these SUMI indicators. Accessibility for mobility impaired users may require some geographical information system data, accessibility infrastructure inventory, public transport asset data. Let's see, the air pollution maybe are simpler, because now with smart cities, we have a lot of sensors in the city about traffic, about air quality sensors, but also we need population statistics that may vary from different people. Noise maps, also in this case, you need some GIS processing capabilities. Road deaths, so fatality rate for 100K inhabitants, like road crashes database, mortality statistics. So a lot of heterogeneous data sources that need to be integrated in order to compute these KPIs that ranges from social, environment, safety, performance, and energy as well. So these are pretty complex indicators, but they have a clear overview of the mobility of a city if computed. We are proposing this SUMI manager architecture that aims to be a multi-domain integration solution, having data in the platform, both from socioeconomic statistics, public transport, GTFS data, GIS computing, urban network, as well as population data. And this is done via the Snap4City platform that enables the development of this decision support system, this kind of dashboards, where you can enable data computing from heterogeneous data sources and integration, of course, data ingestion to propose an automatic computation of these indicators if you have the data, and data processing via client-side business logic, and so on. This solution is focused on cross-city comparison as well as time series comparability across different periods. The system has been validated in Florence and Pisa in order to assess the functionalities of this system. So we are proposing this urban mobility digital twin about the urban challenge that the smart cities are facing right now. Let's briefly see the SUMI calculation life cycle. Ideally, in the image, you can see a quick snapshot of the infrastructure. We will deepen into it a bit later. So first, you need to instantiate a city device, in order to have data ingestion about the different urban data that we have seen so far. You can trigger the computing of the SUMI in two modalities, both inserting the data if you have available, or pre-computing them based on an automatic data processing and data ingestion system. Fourth point is the rendering that will enable the comparison across cities and in different periods. So let's start with the city operator that can, of course, create a new city behind the scene from the code on the client-side business logic. Behind here, we have a SUMI data model with all of 18 data models behind that will enable the computing of these indicators. Everything is automatically triggered into the storage of Stanford City, where you will have each SUMI indicator for every city that you create. The insert data functionalities will go into these IoT, let's say, entities in order to insert the relevant data. And this insert data functionality, it can be done in the current moment as well in past instance. On the bottom, we have the server-side business logic computing, where if you have a preliminary data model about the geographic information system computing and the other possibilities like statistics that you can get from open data from the sensors, if you have the road network available for that particular city via open source maps, you can automatically compute some of these SUMI indicators, and the other one you can insert the required data, and this automatically process the computing based on what the European Commission stated about the computing of these indicators. Let's go into detail on the proposed solution. Stanford City platform enables the development of these monitoring and management dashboards for decision makers. The functionalities are these. You can select a city. We have an immediate SUMI radar chart where you can assess the situation in that city, as well with some bar plot, seeing the values for all 18 indicators. This multi-line time series plot is referred to the time trend based on the selected city. You can, on the bottom part of the system, add a new city, and via the front-end computing, you can directly insert the values of these indicators as well as computing them. And now we will see some details. This is a bigger one. Now I'm going, let's say, ideally to click here to expand the cities. Now we have highlighted Florence, but on the drop down, you can select the other one that we validated, that is Pisa in Italy. You can select the time zone and of course refresh the city list. So in this case, these are the values for Pisa. And let's focus on S1, that is this one. This is the indicator about the cost of the public transport for the poorest part of the inhabitants of the city. I enable the multi-cross-city comparison. As you can see, Pisa has a pretty good level for S1. Meanwhile, Florence is pretty low. So let's see the time trend because this system enables you to select and deselect the different indicators S1, S6, S11 for Florence in this case. It is automatically updated once you select the city. And this is the trend. It's if you look to it, the data have been, let's say, used with time granularity, with monthly time granularity, and it's pretty low. So the cost of the public transport in Florence is pretty high and ranges a lot based on the computing of the data. So the bottom part, you can add a new city, and once you click on the adding a new city, all the data models are instantiated, and you can start the data ingestion process to insert the data about the first indicator that we deepen it into, that is the one on the cost of the public transport for the poorest percentage of the inhabitants of the city. You can calculate from data or so on, specifying time range. So you need to insert the average monthly income of the poorest 25% of the population, the average household size for the poorest part of the population, and the cost of the public transport pass price. This will submit computing that is automatically updated based on this data via server-side business logic in order to update in the storage of the platform the value. And so this will automatically be represented in the monitoring dashboard. In conclusion, I will go briefly. This is an integrated solution to enable both automatic computation and direct input of these sustainable urban mobility indicators. We have multi-ingestion modalities across city comparison in order to have this urban mobility digital twin built on Stanford City platform, is standards compliant on the European Urban Mobility Framework and guidelines. And of course, I didn't deepen into the presentation, but the platform enables is GDPR compliant, so data ownership and privacy are preserved with the role-based delegation and data management. Thanks so much. I've tried to stay on time. Maybe I've deepened a bit more. So thank you for your attention. If there are any questions, you can ask me. Okay. So okay.
So, because since there are no further questions, I think that this concludes our session. I want to thank the author for the contribution, our technical assistants for the support, and the audience for attending both locally and virtually. The session is now closed. Enjoy the rest of the conference, so we can actually close the session and the presentation schedules.
Bye.
Bye. Thank you.
Bye to everyone.
Deve aparecer aqui outra. Ok. Traduzir a câmera.